3G land, especially in the CDMA-2000 evolution activity, which is now a major preoccupation in the standards organization. It's called 3GPP2. It's 3G Partnership Program 2, because 3GPP1, or just no number, is wide density CDMA guys, which everybody hates. And I have to start with a mandatory disclaimer that this talk based only on the information and data which is publicly available on the 3GPP2 website. That's how you can download it. And the relevant technical committee and the working, it's TLGC, and that's working group 5. So it's a physical layer technical assessment. Here are the references, the relevant documents from this website, which are basis of the talk, so that the information I present here contains nothing proprietary. It's all publicly available, and this industry consensus. Just a little bit of overview of CDMA-2000 numerology, just to get up to the scale. It is 1.2288 megachips per second, the number very easy to represent if you take Walsh length 128 and multiply by 9600 bits per second. That's exactly what you have. And CDMA, every CDMA system, it has a NEFA problem, which is being solved here by deploying the basically closed-loop power control with the rate of 800 hertz and knockdown steps between half dB and 1 dB. Now, in the CDMA-2000 1X-EV system, there is a little bit tricky handling of Walsh space. In normalized anti-5 system, if you're familiar, you are dealing with the Walsh on the fixed length, so the spreading code has a fixed length. Here, depending on the channels and depending on the application, the variable length Walsh codes are used somewhere from 32 and up to 256. The maximum BTS power is a standard 20 watts. The reason for it is being because this technology is evolution path. It's supposed to reuse as much possible hardware, software, and whatever from existing system to optimize for the cost of the deployment. And the maximum achievable geometries are kind of related to signal to interference ratio. It's a, sorry for Qualcomm talk here. It is a Qualcomm terminology. It's basically the spectral, the power spectral density from the base station you receive divided by the background noise plus the interference coming from the other base station. So it's more or less carrier to interference ratio. So the maximum you can get without equalization in CDMA system of such a design is something around 18 dB. This number will be important for us because it puts a limit on what is the high order modulation, highest order modulation you can use for this system. Now there are few, of course, this evolution 3G system doesn't come in the clear space. It's supposed to get some requirement. Actually, I'm sorry, how much time do I have?
As much as you like. So we didn't start at 1:30, we started at close to 2, it's almost 2 o'clock, right?
Okay, so how much, what is the, because people have their own plans and I don't want to keep them.
No, normally
from
speak for in the neighborhood of an hour.
An hour, okay, good. So, first of all, the requirement, one of the biggest speech for the technology is to get something like 3 times more voice users compared to ICE95, which will be on the order of magnitude for kind of average traffic model, something like 30 to 36 voice users per sector. That's the goal. Also, there is some weight requirement that one's supposed to get the data in as much as one can, but not lesser than to support important high-rate applications like video. So it means something in the order of from 64 to 128 kilobits per second per user who wants to use the video over the air.
Is it 3 times in the same bandwidth?
Yeah, it is in the same bandwidth. Yeah. As I said in the numerology section, that nothing changed, so it's the same bandwidth. It's just 3 times more users per carrier. So it's in 1.25.
I don't understand why is 3 times higher if the bandwidth is the same.
Oh, well, because suppose, the claim, which is actually true, that IS-95 is not that spectral efficient. So if you modify the system and make better, more intelligent design decisions, you can actually increase capacity by several times. For example, IS-95 on the forward link doesn't have the fast power control. So by just having fast power control in forward link, you have 2 times the capacity easily. Also, in IS-95, you don't utilize any transmit diversity. In CDMA-2000, you have so-called STS, space-time spreading. So with this diversity, you basically combat fading in much better way. So one-pass fading is not... In IS-95, single-pass fading was a killer. The system can support not more than 4 users on the single, if they're in the single-pass condition. With STS, any single-pass user becomes now 2-pass user. And due to this transmit diversity, the requirement for abnormal flow for this user is much better. So there is room. So this number, at the end of the total show, one comes pretty close already. So even in not optimized system on the voice side, one comes pretty close to that. With the data capacity, there are more questions than answers because the data traffic, there are various of types of it. So FTP is very easy to accommodate because it has no delay requirements. You can wait for as much as you wish. But for something like real-time video, near real-time video, it's more closer to the voice service, so the things get really messy there. And of course, there are, actually this number 3 is also not very technical. It's more, again, marketing. The whole thing is very political. The marketing is pretty much intertangled with the technology here. And the cost effectiveness of this evolution played actually more important role than all the technical aspects altogether. So it has to be real evolutionary path. You cannot say, okay, I just scrap entirely and I just start to build a system anew because RF portion is supposed to be the same. A lot of the channel elements in the base station, call processing and so on, supposed to be somehow connected to its predecessor so that the cost of upgrading the system are not staggering. And I just want to outline a little bit some specifics which stem from the fact that you are trying to put voice and data within the same shared resources, namely power and the bandwidth. So being evolutionary technology, CDMA-2000, 1X-EV-DV opted to continue on circuit switch voice. There are several reasons to do so. For example, one is that still probably the industry consensus, well, at least, I don't know, it's hard to say, different people have very strong opinions in this regard, but I think that circuit switch voice still has higher capacity than voice over IP due to less overhead and the elimination of scheduling problems. Of course, the additional advantage is a low complexity because circuit switched is much easier than packet switched. Non-design evolutionary paths, it's all speak for this thing. Now, disadvantages are also obvious. First of all, you cannot extend the real-time voice to any other time or to any other type of real-time traffic because the voice is a low-rate application. The only thing you can do to send video over the circuit switch voice just to allocate the user pipe, or to allocate the voice user a pipe of, let's say, 10. The video user will become like a 10 voice users piped together, which is certainly not the best way to utilize the resources. And the high network complexity to handle both circuit switched voice users and packet switch route over the shared resources. So when you have two, so some users are power controlled voice users, some users are rate controlled, it's a data users. So you basically assign them different rates depending on how good these users are. And interplay between these two distinct type and contradictory requirements within the same frame of constraints isn't really easy to achieve. And that's the topic of the second, another slide, that when we decide to share the power and bandwidth between these two distinct type of users, what are the advantages of it? First of all, higher trunking efficiency. So what it means that suppose in the morning all of my users talk on the phone, but at night they all browse the web. So if I have two separate systems, one for voice, another for data, in the morning my voice users will scream for drop voice, and at night my data users will get any throughput. And at the same time, the other carrier in the morning will be empty, and in the evening the opposite one. So here, of course, the resources are shifting dynamically from voice to data and backwards. That's certainly increases trunking efficiency. And for the carrier perspective, of course, if they have already spectrum available, they don't need to buy anything else or to do the clearing or consolidation of existing spectrum and so on. The disadvantages, the first one is the design complexity to put two networks into one resource allocation scheme. And for example, if you're familiar with the HDR type systems, that's a Qualcomm data-only system. It has the advantage, like for example, mobile drives what rate it wants, because mobile measures the signal from the base station, so it basically knows what kind of the SNR, signal noise ratio it receives. Also, it knows what is the power available at base station, because base station always sends 20 watts no matter what. It can compute itself what the rate base station has to send to it, so that there's a good probability mobile can decode it. And then it sends back the so-called data rate request. Now, in this system, I want to point your attention, you cannot do that, because the mobile certainly knows what the signal noise ratio is. It doesn't know what amount of power is available to the base station, how many spreading codes are available, because there are these voice users which have the higher priority. These voice users take power, these voice users take voice codes, and mobile doesn't know that, so the base station knows whom it serves. So therefore, what mobile sends back is basically measurement of signal to noise ratio, and says, well, now just do a magic and then send me something. But when base station sends something, it also has to send in some control channels what the rate is, or the coding regulations, all the service information, which, for example, in data-only system was assumed that if mobile requests some rate, at least it knows how to demodulate it. And here, base station has to basically channel back to mobile all the service information, which stems from the fact that mobile has a very limited knowledge of what is going on in the system due to the presence of the voice users who nobody controls. And yeah, that's...
What's FL? FL rate data request? It says design mobile collected a FL rate data request.
Mobile cannot send out forwarding. Yeah, that's again, well, maybe few rules for mapping. Forward link means down link, and reverse link means up link. That's a simple remapping rule. Yeah, and another problem is that the sharing of bandwidth becomes also a little bit messy, because the spreading codes, the voice codes, you have to allocate them for the voice users, and also you need to have them for the data users. Now the problem is the data users take contiguous chunks of this voice code. So if I have a voice user sitting somewhere in the middle, the whole chunk is not available for the data. So once in a while the system has to kind of consolidate and move all the voice users on one end of the voice tree and clear up the shorter washes available for the data users. Oops, okay, that's here. And here are the continuation of our review on the key aspects of this system. First of all, the marketing-driven requirement. It's the 1X-EV-DV supposed to be 100% compatible with CDMA-2000 systems, so with the existing ones. So that if I have an old mobile from CDMA-2000, but it's not very old. It's still being from the design board. Well, Koreans, they already run them. Anyhow, if I have just standard CDMA-2000 release a mobile and I enter this super duper new network, I still can use my cell phone to place a voice call. So the voice layer has to be at least backwards compatible. Now, the another very natural requirement for the data service in this kind of designs is that the packet size are fixed. So there's some kind of predefined packet size you send over there. You cannot send any weird number of bits at the same time. And here the flag rates from 384 to 3840 bits per packet. It's not IP packet, it's a physical layer packet. So there are several layers here, and that's the lowest layer 1 stuff. Now the packet durations is variable, so this system is actually very different from what everyone has in CDMA-2000 and even in the HDR, because to accommodate the variable channel conditions, one deploys here all sorts of things, including variable coding rates, variable repetition rates, interleaving all sorts of things, and the variable lengths of the subpackets which result from it. From 124, it's basically by a factor of 2, from 1.25 to 10 milliseconds. And another distinct advantage, which actually, well, distinct design feature which has to be here, it is that, of course, one has to use the channel-sensitive scheduling, because if you have all these varying channels and you have multiple users, it's very beneficial to use multi-user diversity. So if I have 10 users and one user is certainly better than the 9 others, I would probably send this one user first. Now, on the other hand, I can't play this game all the way through, because in this case maybe there's only one user which I serve, but all can pay. So I need to give them some kind of a fairness. And the scheduler, which is in CDMA-2000 1X-EV-DV, so-called proportional fair scheduler. If somebody is interested, I can cover it after the talk. This scheduler basically gives you a asymptotically equal share of time on your channel. So it doesn't guarantee you that you get the equal throughput, but it gives you it. And there is the quasi-complementary tool called channel interleaver, which I said is basically the way to shuffle the systematic bits separately from the parity bits and nicely place them in the chunks which correspond to the slots. And there is a symbol selection part, because on different, it's incremental redundancy stuff, on different subpackets, virtually when we do the transmission, it's not, we are not repeating the same symbols. It's not replicas. So the second subpacket is not the replica of the first subpacket. In the first subpacket, let's say I send the systematic bits. On the second subpacket, I send the first portion of parity bits. If it's still not enough to recover, then I will send the next portion, and so on. So not only I'm gaining the SNR, I'm also getting the changing the code rate, so that coding game becomes larger. There is a scrambler here, which basically adds the user-specific information. So even with the A, well, I think the A is kind of the boundary case, so that by error in by phase jitter, this 16 PSK, you can very easily make a false decision on what this, on what point was in the constellation, was in the constellation. Chrome is more reliable, I think.
But if we use a parity and chill, then how we identify the different amplitude for them?
How is it again?
I mean, if we use parity and chill, how we identify the parity and chill? Parity and chill.
Oh, parity and chill, okay.
Right. So, because we have different amplitude for thinking that.
I don't think the power control tracks the amplitude of the symbol.
Power control is, you have power control is 800 hertz. So basically you have up-down commands at the end of every slot. So within a slot, you can pretty much assume that not only the transmitter power is constant, but also the fading process is pretty much flat. So it's pretty sure. You see, we are talking about Doppler frequencies of up to 200 hertz. and the slots were up 1.25 milliseconds, so that's 800 hertz. So you have a
So within one symbol, we didn't have much phase, so.
from one symbol to another, you can say that the amplitude didn't change. So you can have the symbol, but you can have the situation, the whole slot is in deep phase. But you can't have the situation that two consecutive symbols have vastly different amplitude. Very unlikely. Besides, there is an interleaver which somehow smoothes out all these fluctuations due to fading process. Now, the reason why, for example, usually I was expecting the question why it's 16 quad, why not 64? The reason is that all the measurements point to the fact that the maximum achievable carrier to interference ratio is 18 dB. So with 64 quad and no equalizer, it's just not going to work, even with the telescope modulation. So 16 quad is pretty much what you can do. And here, basically, the simple DMAX with IQ pairs, and here is the multi-code from, here you overlay from 1 to 28 washes, doing multi-code, sum them together, and continue to the sum them together and continue to the next slide. Here, one has this block, which is channel gain, which comes from the power control or whatever, so that the power bookkeeping is satisfied. Here, from the other parts of the system, it has other voice channels, mostly voice channels, common control channels, pilot, and so on. Then there is a final voice chip summer, and here is the thing you asked about how one treats the in-phase and quadrature components. They use two different PM sequences, and then baseband filter, up conversion, and antenna.
So in previous system, you use the same like long mask.
Yeah, that's pretty much. Well,
not long mask for a user, but for the.
Oh yeah, that's the same. That's the same piano as the RS-95. That's the same 15. There's a piano with 15 taps, shift register, and 512 offsets for different sectors.
Okay, the question is following that. You said that the AAIR is the most difficult part. And I'm just wondering, if that rate 1/5, the coding rate, is due to the full time rate transmission?
No. The rate 1/5 is from the design of the turbo code.
Yeah, I know, because you said the first time you transmitted actually systematic message, right?
Yes.
That you do retransmission. I heard you said that the full time retransmission.
Well, the number 4 actually is related to number 5. So I would say the turbo code was given with the rate 1/5 because it looks like it performs the I mean, there was a lot of efforts put into designing the right implementation metrics for this code, so it looks fine. Now, there is the decision to use 4 retransmissions altogether is of course tied to the fact that you have one block of systematic bits followed by 4 blocks of parities.
So they won't go to like you transmit it first time, and the next time transmission, they won't do new encoding based on.
No, there would not be new encoding. There would be. I have a sequence of one frame would be 1,536 symbols. So first chunk of the symbols I send one. The second chunk I send another time, and so on. So I wouldn't do really encoding again, but I might do the remodulation. So coded symbols would not be changed, but the modulation symbols might undergo some changes. Actually, I know oops, time is going very fast. So, but that's actually the what is called quasi-complementary turbo code interleaver. That's systematic bits which go just straight here, and there is some interleaving between them, just as a channel interleaving, and now the parity, there's a parity bits, they are interlaced one between another into these chunks, and here how the incremental redundancy works. So if I send this portion only, my effective code will be 2/3, and that would be used for users which are close to base stations so that their data rate is very high. And if I fail, then I will send the other portion so that my rate becomes lower to 1/2, 1/3, and finally if I send all the symbols, I will recover all 1/5 rate turbo code.
Question, do you need to assume the channel is spaced over the 5 blocks, these 5 blocks?
Actually, the boundaries between these pieces when they come over the air are very flexible. The base station will decide actually how to puncture and what to send when it has information about signal-to-noise ratio. So there's no hard boundaries like five fixed portions. Let us postpone your question because I think I have a whole slide devoted to it. So that's, I think I covered already, that's the primary packet data control channel, which is optional, no much of the excitement anyway. Now that's the secondary packet control channel, which sends MAC ID, and now it controls the ARQ. So 2-bit ARQ channel, so that every user can have up to 4 outstanding ARQ transmissions in place. Now 3-bit encode the packet size, which is to state how many bits I have in the packet, and 2 bits of packet ID, which numbers the sub-packets within any retransmission line, and 13 bits per end slot. So this secondary packet data control channel is variable length. It can take 1, 2, or 4 slots, depending on the channel condition. And it's standard convolutional encoded rate 1/2 constraint X9 code. And it has a symbol repetition, basically nothing really exciting. Probably I will move on to something more interesting. And it has a Walsh length 64 spreading. And its operation is basically, there's only one interesting point here. It's the length of this packet supposed to indicate the length of the data channel. And the mapping is almost 1-to-1. So if the length of secondary channel is 1.25, then the same length is the data channel. But this guy doesn't go anywhere beyond 5. So 5 is the maximum length of the secondary channel. At the same time, the data channel can be 10 milliseconds. So there should be a way how one can distinguish between the case of 5 and the case of 10, which are both represented by 5 millisecond channel. The way to do it is to reinitialize the CRC differently. So the initialization of CRC for the lengths 1.2. So this guy, and this guy are being mapped into this channel. There's a CRC initialized to all zeros in the tap delay line. Now, this particular guy will be mapped into this 5 millisecond secondary channel with the CRC is initialized to all ones, so that one has 2 millisecond frame and checks 2 hypotheses with one CRC and another CRC. This is a way how you can convey some information without spending extra bit to pay for it. So the 3GPP2 is cheap. So they conserve every bit on cap. And the rates are different. Of course, it's variable length, also variable code rate, that's natural. And the 5 millisecond rate 1/4 is pretty strong code, pretty low length. So in this case, the user at the edge of the cell has a pretty good chance to decode. This channel is very important because if you can decode this channel, that's it. You cannot decode the data packet. Well, that's everything I think self-explanatory. Now, and that's how it works. So this primary packet data control channel basically tells you only the length of your secondary packet data control channel. And that's optional. So probably in the real life, there would be no such indication. So what mobile will do, it will just try to decode the secondary channel under four different hypotheses, 3 different lengths, 2 different CRCs for the last length. And then this big chunk of the data in the packet data channel falls. So pretty straightforward. So there is two layers of redirection of the service information here. And the Walsh information, again, so if the MAC ID is set to all 0, it's not a real MAC. It just tells that everything follows, indicates you what Walsh codes are used. And here are 24 possible, as I said, it's a multi-code, 28 out of 32 Walshes for the data. And that's exactly which ones are used and in order. I probably skip I think it's a little bit repetition of what kind of reverse link channels, just two of them, for the acknowledgement and channel quality. That's how this, so there are both, actually the first channel is block coded, 5 to 12 code, and it has a Walsh spread, but it's not for multi-user, it's just to separate one channel from another, as one does on the reverse link in CDMA anyway. And the second channel is not 12, it has a repetition coding with a 24, factor of 24, so nothing really exciting. Here are some statistics on the utilization of different payloads in the system. So we have 1, 2, 3, 4, 5, 6 different rates, and how these rates really, if I have some kind of average traffic model, channel model, and I just put the queuing buffers are always full, and I'm basically trying to see what my scheduler will allocate in terms of the size. That's the distribution. So if you sum the numbers in every column, you should get 1. So it's a probability normalization. And you see then, of course, if I have a very little payload, 384, then overall it's always enough to send just only one slot. So it would be enough power per bit to decode it. As the length increases, then of course the 2-slot and 3-slot and sometimes even 8-slot sub-packets become more common.
Is it everyone clear on why? Am I the only one who's not clear on why?
Well, because the energy per bit, if you keep the length, suppose I keep the length the same on slot, but I keep on increasing the payload, the energy per bit goes down because I'm power limited. And if energy per bit goes down and I send it out, the probability of error will increase. So the next retransmission, the base station will decide, just let's increase and let's send 2-slot sub-packet rather than 1.
Well, they behave steadily, but the second one, like 2 slots, why does it have a peak at 304?
Pardon me?
And then goes down?
Which one?
When you look at the payload size, the slot 2. Why does it have a peak?
Oh, this was the slot 2. It goes.
I mean, is it just some idea behind it, or just the simulation showed it?
No, I think that why it goes down from 4 5.
Well, if you can see, it has a peak on that 3D plot at 2304.
Oh, you mean this one?
Maybe looking at the row and the table.
Which one? 2-slot row and which form? This one?
Yeah, exactly that.
Okay. It looks like because you see that's for a specific traffic, for a specific channel mix. So it means that you have different users, which actually is a statistic quality, so it's not per user. It's just all the users thrown in, and there is a kind of average C2I which you have. And what you are doing, you basically what scheduler is doing, tries to match the SNR as close as possible to what is being measured. And it just happened that for this particular 2-slot, that overall, the combination of 2-slot lengths and 2304 bits per packet matches this particular SNR probably the closest. So that's why this probability is higher. Because this is probably a little bit overkill. So here I'm wasting a little bit energy because I have 2 little bits to send. And here I'm probably a little bit underpowered because I have too many bits. So that's an optimal point. I think in every row you have, in every row you're supposed to have a peak. Just maybe we don't have enough rates. So if you have like infinite number of rates to every direction, for every length you will have a point which is optimal for this particular SNR measurement.
I understand that you have this problem like this if you have an energy kind of a constraint.
Yes.
I'm just curious why the forward link you care the energy constraint, the base station, why you care that?
Well, because I have voice users which take the energy, so my energy limited. Actually, here data only, so I have 20 watts.
Because you said one user at a time, right? Only for the data is one user at a time.
Only for date is one user.
Fine.
Yep.
Thank you.
How do you, so when you keep the payload the same but you change the packet duration, so are you changing the spreading gain or the
Yes.
modulation?
Well, actually modulation. Not coding. So it's basically the code. It is a rate 1/5 code with a proper number of punctures and repetitions if necessary. So if I need to go to the code higher, then I do puncturing. If I need to go to the code lower, I repeat the symbols. So it's okay. Now that's this is a similar plot, but that's now not for the full buffer case as it was before, but for some realistic type of traffic, warp HTTP, FTP, and then RV state for real-time video. And here you see that the picture is a little bit different. So for video, for example, we have a spike here for the single slot because the video is supposed to be delay non-tolerant, and here one puts extra efforts in the scheduler to really account for this.
So are you saying that actually you have a scheduler which somehow knows the names of these three times, and then the traffic streams are classified by those, and then it somehow tunes itself?
Well, there are actually two aspects to that. That's one. The other is the offered load, because the offered load also reflects the service type you have. Because if it will be NRV, then it will be rapid succession of the fixed size chunks which are being placed into the queue on the entrance of the scheduler. So if the offered load is equal to the throughput, there would be no backlog. So the scheduler will always take the only chunk on the line and move it out. So the size of this chunk will somehow hint scheduler that there is a specific real-time traffic. So even if there is no IP bit which says that it's even if the scheduler is not allowed to sniff into the packet content, it still can make some guesses, intelligent guesses, based upon the offered load and the rate of the packets income into the system.
So when you draw this chart, one aspect of this chart is that those different packet traffic classes have different packet size characteristics or not?
Pretty much, yes. So this chart is more for the carriers, because for the carriers it's important to know, at least they want to see the real type traffic displayed on the simulation results. I don't know how much one can really learn from it.
Yeah, okay.
So the only evident thing here is at least that all slots are occupied. So there is no unnecessary redundancy. So we are not designing something which is not being used. So there's all the slot combinations are being populated with some non-zero probability. So let's say that's a major result. Now, what happens if, let's say, voice cuts in the power and voice and the Walsh? So that's pretty much the same picture as I showed before, but just now everything is being shifted a little bit below. So now the fraction of the longest slots is now higher because less power available, so one need to send longer. And the same thing for the different type of traffics. Again, it's very similar to what we saw before. Unfortunately, it's not easy to compare two graphs because they are not at scale. If you notice here, the probability is 0.7, and here the probability is 0.45. So the plots look almost the same, but just one scale version of another. So they should be plotted up to the same scales on both axes. Oops, I'm really off all my time. Okay. Okay, now a little bit about the modeling of the system, because everything's supposed to be simulated up to pretty high details. And one of the very tricky things, how one simulates C2I in this CDMA design, especially taking into account that there is some losses of power in the left portion of the receiver, as well as a result interference coming from the multipass cases, so on. Therefore, the model which was chosen is a so-called array model. So we have n arrays, and every array has a gain of gamma. There is also one extra array which is called lambda, is a fake one, it's bogus, it's not existing. It is basically to account for the unrecovered power. So unrecovered power is being modeled here as having some extra interference placed into the system. So instead of lowering the power and increasing the interference. And so G minus 1 is the geometry. It's basically the total received power from a base station divided by thermal noise plus the power from the other base stations. And that's how this thing is defined. And this parameter is, because of the presence of this lambda, it is limited to, let's say, 13 dB or 18 dB, depending on the channel conditions. Have a go here. That's the channel model mix which is used in the simulation. So there's pedestrian as well as vehicular models, as well as some ration, so some static users with a direct line of sight which has a ration factor 10 dB. And there is a probabilities for all of them. There is a little bit interesting point here. At speed of 120 kilometers, one uses pedestrian A model. It's not a mistake. It just happens to be that in reality 120 kilometers per hour is indeed the case, which can be described pretty accurately with pedestrian A. And that's the finger assignments which one found over long studies with MATLAB is probably the optimal one. So how one places the finger, so there's finger delays as well as the finger gains. And FURP is abbreviation for fractional uncaptured received power. That's what is this fancy name, fancy name for this parameter lambda. So that's the one which actually is responsible for the fact that you never really get beyond 18 dB carrier to interference. And here are some of the results on the, for example, voice capacity. So how the voice capacity is being defined here first. That's based upon the voice quality of service. So the thing is such that you hear the conversation goes fine if you have not more than 1% of the frame errors per conversation. And also they should not be too clustered one next to each other. There is some empirical model which kind of defines the acceptable quality of voice for digital recorders. It's based upon the so-called voltage indicator. So you have a window of 20, so a frame, voice frame in CDMA-2000, 20 milliseconds. So you take a sequence of 20 frames, which will be like 400 milliseconds, and you compute how many erased frames you have there, so on the current frames. And if this percentage of these bad frames over the window of 20 is about 15%, you declare this voltage indicator to be 1. If not, then this indicator is 0. So it's random variable, binary random variable with value 1 and 0. Now, if the lifetime average of this indicator is more than 3%, then this user is dropped. And this actually system voltage rate is the average rate of the system of these voltage indicators in this particular drop, so in this particular simulation. And the capacity is being defined, I think, by this 3% line over here. And it reads with STS stays for the space-time spreading. So it's basically transmit diversity when you have to transmit antennas. And it looks like for the radio configuration 3, which is what I call it, it's CDMA-2000 notation. I really didn't cover them in all details today because of the lack of time. You have 22 users, and you have 18 users for a rate 1 half code, which is also understandable. It's microcode. And in the beginning, I mentioned that we need 36 from the marketing. Now here there is one caveat here, that most of the channels here are single pass fading, or very close to it. That's because you have pedestrian A is very bad, and it's represented here twice for the 3 kilometers and 120 kilometers per hour. And it has 40% of the probability to put a user into such awful situation. That actually brings the thing pretty much down. So for different channel, therefore these numbers are pretty much conservative. If you have some better channel conditions, like in real life, you have, by the way, much better single pass is not typical case in the real life, because if it were, then ICE-95 would fail completely. And since we can talk about ICE-95 network is just proof of the fact that single pass is not that common. And that's a voice. And I would like to proceed further to more interesting part, which is the data capacity.
Is that really true?
Tell me?
If IS-95 is the
Four
universal
users.
single path,
4 users per section. That's all. That's all of them have. There's a single pass.
is there some assumption that there's that it's single path rarely fading?
Yes, of course. Well, sorry. Of course, it means single pass rarely fading. So, of course, everything when I mentioned single pass, there is implied second part of the sentence, which says single pass rarely fading. And it really makes the system
incredible, Martin.
Yeah, of course, single pass in WGN is the best you ever can do.
Right. If the alpha theory works great there, and I don't see where 4 pops out.
No. It's rarely fading single pass. Sorry. Basically, here is the data capacity for the clean cases, not the mix, but specific. Again, all the cases are really fading, 3 kilometers, 30 kilometers. So it's all really fading cases. And here one sees two basically limits. C2I is limited by 13 dB, and C2I limited by 17.8 dB. That's due to self-interference. So different scenarios allows you to go only to 13 dB or to 17.8. With 17.8, you can have some users utilizing 16.1. That's actually the explanation why their rates are higher by something like 10%. And there is also system throughput for, these cases are like full buffer traffic, so there's always something offered to the system. Now, for the real HTTP case, when you have all this reading time, waiting time, all that stuff, but you have 44 users, so that your statistical average network offered load is 730, you get to the throughput of 1724, which is kind of balanced. So your backlog doesn't grow up higher than 6 kilobits per second.
To a viewing person, that makes no sense at all. Right.
Well, of course, it's very bad. But you see, the reason why is that because that's how it goes in the simulation lab. So you are starting with one user, and then you are placing as much users as you find as your network starts to backlog. And it just happens here for this length of the simulation that there is a small disparity. So if one runs it for infinity, then of course one shouldn't write here 44 users and this, one should write here 43 users, and throughput should be always larger than average offered load. But
they can never be larger.
Well, not larger, but I mean they should be equal, but I mean the potential. So the bottom line is that the maximum throughput should be larger than the offered load, so that the system is stable. So there's some room, if there is fluctuation in the offered load, the system should be able to accommodate it. And I would like to conclude the talk by some study items and the components which are on the table. So one has the different modulation scheme for the transmission, so they're still working. Enhancement to incremental redundancy, especially in the terms of how you combine the sort of decisions which you receive from different modulation schemes. 64-QAM is always under consideration, but this might require some equalization because you have 18 dB limit which you can reach without equalizer. And for 64-QAM, you probably need something 25 to 27 dB. And that's what equalizer can give you. And also there is a big outstanding problem for VoIP users who love to send very small packets over the network of the size of maybe actually it should be of the size of maybe 100 bits or 200 bits. This system can handle the smallest is 354. It means that it will be padded. If anything smaller, one padded with 0, which is certain waste of capacity. There is a fast cell selection because, as you probably noticed, there is no soft handoff for the data users here. So one doesn't utilize this kind of diversity because it's very wasteful in terms of the wash resources. And instead of it, one can try to switch very fast between the good service for this mobile. Also, subslots, if I divide a slot into pieces, then one can put 2 users. So if I have 2 WAP users, both of them have smaller than like 100 and another 100 bits, I will pack these 2 distinct users into one sub-packet and send it over. Adaptive antennas and multiple input, multiple output stuff to get real high data rate. That's in support of 64 quad. Oops, that's all.
So if you had a do-over, there's some parts people say, no, we would do that totally differently.
Let me put it as follows. 1X-EV-DV, first of all, in my opinion, is the last design which uses switched circuit for the voice. The reason why, there are several reasons why it's done this way. Mostly not because of the technical stuff, but because of this evolutionary path. It's supposed to be an overlay over the existing CDMA-2000. So if you keep this design requirement in mind, I don't think there is much of the breathing room to redesign it any differently. It might be in some details, but overall, the basic things of utilizing the channel variation, channel sensing, this asynchronous retransmission, incremental redundancy, instead of just, let's say, chase combining, it's pretty obvious solution. Now one can argue specific, maybe little things like 3 bits instead of 2 bits, more already, 12 rates instead of 8 rates, but pretty much there is not much one can do otherwise for this particular overlay of existing CDMA-2000.
Just wondering when this one has been finalized.
Actually, probably by the middle of next year, I think it will be out from the 3GPP to So it's already in pretty good shape in terms of the overall design. I just need to figure out a few things, make a complete simulation, get performance back, and I think based upon my experience with the standardization of CDMA-2000 and HDR, after the system gets in this kind of details, probably a year is enough to have all the process completed and to have like first release out. Then of course there will be some revisions A, B, C, and so on, but the first shot.
What's the next after the CDMA-2000 for Coca? Is there any new?
Well, it's okay. Let me show the disclaimer.
They haven't said what's next on the 3GPP.
I cannot tell you anything beyond what is publicly available. Sorry.
You showed two coding schemes. One of them for motion, the other one is for one channel you showed they use turbo coding. For the other channel you showed they use convolution coding.
You mean this? You mean the turbo code is used for the data channel.
Yeah.
Now the convolutional is used for data control channel. So data control channel is only 13 bits. It's a service channel. It's auxiliary. So the data is being turbo encoded.
Yeah.
But there is a service channel which basically tells you what is the frame size, what is the coding rate used, so that mobile knows how to decode the thing. It's only 13 bits plus the MAC ID. And with the turbo code, it's just too much processing power, you will. And besides, the turbo code, the biggest advantage of turbo code, that effective block length is huge. So if you design a turbo code with the length of, let's say, 20 symbols, its performance will be much worse than convolutional code. Convolutional code can stay next line, you have the turbo decoder, which is the optimal decoder. And turbo code is suboptimal in the first place. So it beats, it beats the Viterbi not because it's a better decoder. It beats Viterbi because you cannot build Viterbi decoder for the convolutional code of the constraint length, let's say 200. You see, and that's why.
So the constraint length is high. You are encoding 32 bits.
Well, but there's
Do you flush the encoder?
Hmm?
Do you flush the
Yes, with 8 bits. That's right.
So 1/3 of the information goes to flushing.
Yeah, but that's still it aids your decoding because you know the starting point on your trails. It's already in some knowledge about your sequence, so you know where to start. No matter what you receive, you just fill 8 bits blindly into your decoder right away.
Yeah.
Of course, it's also there are some ways here because the constraint length 9 means that the effective block length is 2 to the power 9, which is 512. So it means that you're supposed to feed 512 bits in instead of 13. Well, 13 plus 6 for max or whatever, it's under 20. But it's much less waste than if you do the turbo, and this turbo will have lesser performance because it's suboptimal. Convolution, the Viterbi algorithm is maximum likelihood, so what you can do better.
Yeah, I did my research on convolution for the turbo coding.
Oh, good.
I have another very weird scalability question. The thing is, right now, actually, due to 911, there is the issue that Congress asked the company to offer special code for the government to use, and actually users don't want it because probably in emergency we want to contact. So actually, Verizon say right now they offer very large capacity, but I do not know than actually needed in a normal time. So I just wonder whether this kind of consideration can be embedded into this kind of a system.
I really think that the carriers, no matter what they say, but I believe they have the capacity problems already. They don't have any excess capacity, if I understand. So, and their interest to this system is actually due to the fact that we can offer like 3 times more voice capacity. Because the carriers are very reluctant to buy into the data services because it's an uncharted market. You don't know how much you can charge and how much customers are willing to pay. But voice is pretty much known. You can expect how much you gain from every voice user. And one of the selling speech for this thing is that you just increase your voice capacity almost for free. Now, and just let's start and operate as a voice-only system. Now, if at some point your customers will demand some data service, you just need to push a button. There is nothing else you need to do. And your voice and your data will kind of start occupying some resources and you will provide the service. That's a major idea because with a data-only case, the carrier has to allocate a couple of $1 billion just for data. It's very high-risk operation because if they can't subscribe data users, then they're stuck. Here, if you refer to subscribe data users, they have a rollback. A very safe rollback. They will say, okay, let's continue with voice and offer some kind of tweaks like from the data portion they can offer web service, messaging, some cookies and so on. But you never know how really the market will develop after September 11. When it's some back channels over the ground monitor every fall.
I guess somehow what happens here is you spend all of your time talking about the data, but the reality is you're saying it's 12 to 22 or 36 of voice that really matters. And I have to admit, I don't quite see where all of that is coming from, because for the voice, it looks like sort of fairly minor tweaks on IS-95.
I would say in CDMA-2000, the biggest tweaks, and actually
because it's still all, right?
1X-EV-DV for voice is exactly CDMA-2000. Now, how it differs from IS-95? First of all, there is, there on the forward link, there is a fast power control.
Okay, that's 3 dB, I guess, right?
No, much more. It depends on the channel.
Is factor 2, right?
Yeah, but for the single pass channel, it's probably 5 dB. Because SNI, without power control, you have to allocate a huge margin. So single pass relay fading, in IS-95, you should get, you should target, so you should have something like 13 to 14 dB of SNR. This power control is requirement in order to have 1% frame error rate. For this power control, fast power control here, 7, 8 dB will be sufficient. So
that's almost all of the 12 or 22.
Yeah, because the requirement is 1% FER, so the deep phase has to be combated. Otherwise you get 3%, and that's already very poor service. The second thing is in CDMA-2000 radio configuration 3, there is the fold rate is a conventional fold rate 1/4. In IS-95 it was rate 1/2, which also gives probably 1.5 dB in addition. On the reverse link, there is a coherent demodulation of the reverse link, so there is a pilot. There is a reverse link pilot. So in IS-95 there was no non-coherent. That's why one gets 3 dB.
Right, because otherwise you don't prove the reverse link, right? You're going to get into an overhead forward link.
No, actually the IS-95 as well as CDMA-2000 are still forward link limit. That's why everybody talks about forward link. Reverse link, in a sense, is in a good shape already.
Right.
And it always was. So IS-95 is forward link limited, and CDMA-2000 is always, but not that severely.
Well, the thing was, when they originally designed IS-95, they thought it was going to be reverse link.
Yeah, the original design said that it would be reverse link limited.
Right, and then soft handoff sort of, I think, turned out to be better.
There was a misconception. For pretty long time, forward link was considered to be orthogonal because it uses orthogonal Walsh codes. In reality, forward link is not orthogonal because of the multipass. And the initial papers, I think, they were making a mistake that they were treating the capacity of the reverse link, of the forward link as pretty much orthogonal channels. Now, if you put the multipass, if you put this all together, then you will see the actual performance of the forward link is worse than the reverse link.
Right.
Just one question, actually, it keeps confusing me. The reverse link IS-95 is offset QPSK.
I think so.
It's offset half the symbol QPSK. So how does it uses non-coherent demodulation? Actually, you need to know the phase if we have the same definition for coherence. I mean, if you don't mean you have like a PLL, but you use like the Walsh code alignments to get the phase, but anyhow you're getting the phase. Otherwise, you cannot detect.
If you don't have a pilot, well, you can do the correlate. You can still run it correlate with a matched filter. But how are you supposed to? You certainly know the relative phase of one thing relative to the next symbol.
But
how you know the
coherence means you're actually not.
Coherent
Coherent means you know the phase.
Yes.
Non-coherent means you don't care about the phase.
That's true.
If you're tracking the phase changes or the absolute phase or whatever in like QPSK, then you need to know the phase anyhow, right?
I think the phase
Well, maybe I'll ask a different question. Is the reverse link now not going to be this orthogonal modulation 6 to 64? The reverse.
I'm not a reverse guy, so I'm not sure.
So they use this orthogonal modulation.
Yeah, they map 6 bits into 64 Walsh codes.
So actually they're tracking the Walsh code basically, rather than using PLL sort of stuff.
Well, you see, if you have security, the non-coherence coming this way. So usually the coherent modulation you can distinguish from positive, like bipolar modulation, you have positive and negative. Here you can't. So what you do, you have orthogonal sequences like 64, and you map and you number them by a 6-bit number. So and then you run it through a filter bank of 64, and then whatever was correlated, you demap it into 6 bits. And that would be not coherent.
Filter bank.
If there's a filter bank of 64 filters, which represent you 6 bits.
Yeah.
So it's certainly not coherent. You don't need phase, and there's certain loss with that because you basically can't have positive and negative. You basically have your plus bit is 1, your 0 bit is 0.
There's something though about, so it is a kind of what you'd call non-coherent, but there's something.
In a way, I guess you know the phase, but there's some really.
It becomes, what it is the phase just becomes a phase of the complex output, and it's just and the magnitude of it is what matters.
Yeah, exactly. Because the phase of 0 doesn't really matter. Out of 64 correlations, only one correlation matches to some non-zero value. So what you really care is that 63 are zeros and 1 is non-zero. Whatever is non-zero gives you a 6-bit combination. Everything else is 0 in the face of all the zero.
In other words, you're using like Walsh's carrier rather than sign.
But it's not a multi-use. It's not really CDMA concept because it's not the multiple access. It's modulation. I would say it's just Wolf-type modulation.
But it's modulation in a very big, I mean, there's a lot of confusion over that because there's definitely all the sort of simulation experiments say that you're carrying more users by doing this big orthogonal modulation in a high-dimensional space.
Granularity increases, so it's supposed to be more dense packing of balls in the phase space.
Hello. Hey, hold on one second. Okay, we have to thank our speaker.